fact that the integral of a to b of f of x dx is equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. Remember, the integral is just the area underneath the curve from a to b for some curve defined by f of x. Find the area under f of x equals x squared from a equals 0 to b equals 3. So this part right here is the area that we are looking for. That's the area that we're looking for. So what we want to do is we want to figure out what is f of b, big F of b, minus big F of a. So big F of x is the antiderivative of little f of x. So the very first step we need to figure out here is what is the antiderivative to little f of x. So little f of x equals x squared. Little f of x equals x squared. When we worked through the derivative examples, we talked about the power rule, where you take the exponent and you move it down. So for example, if we have f of x equals x to the fifth, the derivative of x is equal to move that exponent down, move the 5 down. So we have 5 times x, and then we subtract 1 from the exponent, so minus 1 from it at that point, so it'll be 5x to the fourth. So there's this nice, easy rule for taking derivatives with the power rule. So if we've got x squared and we want to reverse the process, well, since it drops down by 1 each time we wind up taking a derivative, that means that the antiderivative must push our exponent up by 1, right? Since it goes from it will drop down 1 when we take the derivative, when we go to the derivative of big F of x. Remember, since big F of x, we can take the derivative of big F of x to just get little f of x. We have to have this relationship of our exponent dropping down when we take the derivative of big F of x. So the derivative of big F of x, that 3, must drop down to a square, since 3 minus 1 will go down to 2. So we know that the exponent that must start there must be 3. However, if we were to work this out, we'd wind up getting x cubed. If we took the derivative of this, we'd bring the 3 down, and we'd get 3 times x to the 3 minus 1, or 3x squared. But there's this problem here. It's not 3x squared, it's just plain x squared. So how can we get rid of this 3 coefficient at the front? We just divide the whole thing by 3. So we divide the whole thing by 3, and now we have the antiderivative to it. Let's check and make sure that that works. So let's check. If f of x is equal to x cubed over 3, then what is the derivative of f of x? Well, it should turn out to be little f of x. So we've got this cubed exponent. We bring that down out to the front. So that's going to be equal to 3 times what we started with. X 3 minus 1 becomes a 2. It's still divided by 3. 3 on the bottom, they cancel out, and we've got x squared, which is what we started off with. That checks out. Great. So now we've figured out what our antiderivative is. At this point, we can now actually use this portion of the formula. So big F evaluated at what's our b? 3, minus big F evaluated at what's our a? 0. So big F of 3 minus big F of 0, antiderivative of our function evaluated at the far end minus the antiderivative at our starting location. The ending location minus the starting location. So what is our thing? It's x cubed over 3 is what our big F of x is. So we've got 3 cubed over 3 minus 0 cubed over 3. 0 cubed over 3, that just disappears. So we've got 3 cubed over 3, 3 cubed over 3. The 3 cancels this into a 2. The 3 on the bottom cancels our top exponent down by 1. We've got just 3 squared. 3 squared is 9. Nice. And that is the exact same thing that we got by working through that long infinite series method, where we had the limit as n goes to infinity of this approximation. And notice how much faster this was than that previous method. And this was with carefully explaining a bunch of ideas that we've just seen the very first time. If you were used to doing this, when you get used to this method, you can fly through it. You can do it so much faster than trying to work through the limits. That precise formal limit method, that's something that you learn at the very beginning, just so we can introduce this really, really amazing fact. This is the fundamental theorem of calculus. This idea is so important, it gets the name fundamental theorem of calculus. It's really cool stuff here. All right, that does it for this course. It's been a pleasure teaching you. I hope that you've not just learned how these things work and how to use them, but that you've also started to gain some idea of how math works on a deeper, more intuitive level. Things are starting to make more sense to you than they were at the beginning of the course, beyond just the specific material you work, but you're starting to get a better sense of just how math works in a personal way. And even if you don't decide to continue on with math, I hope you've started to develop a little bit more of an appreciation for just how cool it is, how many uses it winds up having. This stuff is really great, and it forms the basis of so much of the society we we have. Just the basis of technology in many ways is mathematics. Plus, I think this stuff is just beautiful and cool for its own stuff, just to study it. All right, we'll see you at Educator.com later, and I wish you luck in whatever you wind up doing. Goodbye.